Hi, I'm Sofia Ferro, a PhD candidate in Applied Life and Health Sciences of the University of Verona, and this video presents a work born from the collaboration between the University of Verona and the UPM ModelFLOWs group within the Meetout project coordinated by the Dr. Alessandro Marconno from the University of Verona. The study is entitled A New Method Based on Physical Patterns to Impute Aerobiological Datasets. So pollen data are typically measured on daily basis by manual samplers, so leading to incomplete datasets due to malfunctions or voluntary interruptions of the samplers. So there is a need for imputation methods specific for aerobiological datasets. Various imputation methods are used to address pollen missing data, such as statistical approaches like linear and moving mean interpolation, and machine learning techniques like convolutional neural network. However, the application of machine learning approaches in aerobiological missing data imputation has still not well explored. As previously seen in other videos of the ModelFLOWs app, the singular value decomposition is a data-driven method able to recognize and extract the relevant spatiotemporal information directly from the data, removing noise and reducing the dimensionality. To address missing data, the Gappy SVD has been implemented. This algorithm used the SVD decomposition properties to iteratively repair and reconstruct the datasets, and it was successfully applied to reconstruct fluid flow or oceanographic datasets, but it has never been tested on aerobiological datasets. In this video, I present a simulation study that we conducted to evaluate for the first time the effectiveness of GSVD in inputting aerobiological datasets, comparing it with a well-known statistical method, the moving mean algorithm. For this study, we extracted pollen data from the Polnet database of the Italian monitoring network by using the Polnet R package. We downloaded data for the period 2018-2022. Then we selected the 2 monitoring stations located in different environments and climates in the alpine and lowland areas, and we selected 2 pollen with different characteristics in terms of load and seasonality, as shown here. Then we calculated a common season period for both pollens, and we selected the season 2022 as a simulation period. So we obtained 4 time series, each for pollen and station. The methods of imputation investigated are the moving mean method and GSVD method. We used the moving mean algorithm from the Aerobiology R package that it consists of filling in missing values by averaging nearby data within a symmetrical interval that is twice the length of the gap. On the other hand, we used the GSVD algorithm of the ModelFLOWs app, consisting of iteratively apply the SVD until the mean square error of the gaps between 2 iterations is low enough. For this study, the GSVD algorithm was initialized into 2 settings: the mean value of the time series with 5 modes and the linear interpolation between values of the time series with 10 modes. To explain how the simulation study was designed, I used a time series example. Briefly, we randomly removed daily observed data from the complete time series of pollen, following 12 simulation scenarios by combining 3 proportions of missing data, 5, 10, and 25, and 4 gap length, 3, 5, 7, 10 consecutive missing days. Data were randomly removed iteratively 100 times so obtaining for each simulation scenario 100 simulated time series as showed here. As a result, we obtain a total of 48 simulations, each with 100 time series for imputation. Then for the imputation, we applied the moving mean and GSVD algorithm on the 100 incomplete time series from each pollen station and simulation scenarios. We calculated the root mean square error for each repetition and for each pollen time series, and we obtained final data sets of root mean square error from all 100 simulation of the 48 datasets. Finally, we calculated the median root mean square error for each imputation method and each combination for missing data. Besides this, we checked if the natural variability of the pollen may affect the imputation process, calculating the variation index. That is defined as the average of the moving coefficient variation over the pollen season. Then we employed multiple linear regression models stratified by pollen and monitoring station to explore the relation between the imputation accuracy and the pollen variability. The dependent variable was the root mean square error from the 100 replications by all the simulations. The results show that the GSVD was as good as the well-established moving mean method. However, the imputation error was primarily influenced by pollen characteristics and location, and the distribution of missing data, regardless of the imputation method used. In conclusion, we introduced and tested a novel imputation method demonstrating comparable performance to the statistical approach and strong generalization capabilities of the algorithm across the different data types. Thanks for watching. If you want more information, please visit the ModelFLOWs website.